Hello and welcome to Let's Code Physics Season 2. I'm excited to be starting this new series with you. We are going to be taking a look at developing a quantum mechanical wave function time evolver. That was a lot of words. We'll just call it the wave function evolver, or maybe I'll call it WFE or something like that. Who knows? So you're probably familiar from some of the basic ideas of quantum mechanics that these things that we call particles that have very definite locations and these things that we call waves that are spread out, they kind of become one and the same, or they become interchangeable. You can think of this in terms of the probability density for each of these things. So for a particle, its probability density is going to be 0 everywhere except where the particle is. We know the particle is right there. Maybe we've got a little bit of experimental error to the measurement, but we can in principle know the particle is right. We can know that the particle is right there, and not over here and not over here. Whereas a wave, if you think about its location, it's actually kind of counterintuitive to think of a wave's location because a wave is nice and spread out. So the wave is sort of by definition everywhere. In fact, it's really the same everywhere in the sense that it's got the same wavelength and the same amplitude everywhere that you go, right? It's not you can move the wave over a certain amount and it looks the same, whereas the particle, if you move this peak from here over to here, it's got a very different look to it, at this location versus at this location where there's nothing. And quantum mechanics says that these two things can actually flip, that things that we thought behaved like waves behave like particles, and things that we thought behaved like particles actually behave like waves. So, for example, waves behaving like particles comes in the case of light. We traditionally thought of light as a wave, as being this nice continuous flowing thing with maxes and mins. It's actually got an up and down wave and a side to side wave, so that leaves you with this EM wave dance that I like to do in class. Whereas a particle is well defined, in this nice location. And what it turns out is that light, under certain circumstances, behaves like a particle, behaves like it's this packet of energy that exists here, but not over here and not over here. And then it turns out that the reverse is also true, that things that we thought behaved like particles end up behaving like waves. So, for example, electrons, which we originally thought behave like these lumps right here, it came in this definite discrete package, turns out to be spread out. They've got what looks to be a wavelength and an amplitude, and they can interfere with each other and produce these patterns that you wouldn't expect from a particle. Now this is interesting and it's revolutionary, but it still kind of reinforces this false dichotomy between particles and waves because it makes it sound like the thing is either behaving like a wave or it's behaving like a particle, when really they're both behaving like a probability density. So, for example, if you think of these two things as sort of the extremes, you can also imagine that you've got a probability density that's somewhere in between. So you might have a probability density that is flat off to the sides, but that then develops some wavy properties in the middle and then kind of flattens out there. Well, I was able to join those lines together there really nicely there on the first try. Good job, Brian. And so it's really this sort of in-between type of existence that we're really interested in, because that's where the really interesting stuff comes into play. So you can think of this as sort of an intermediary case between the particle and between the wave. You wouldn't really say that this thing is behaving like a particle or a wave. It's behaving like something in between. It's behaving like a probability density. And so we have to start thinking in terms of probability densities. We usually represent a probability density by the Greek letter psi, and this probability density is both a function of your position and your time, meaning the point that you're looking at and the moment that you're looking at. So these little snapshots that we have here are actually only valid at one instant of time. So, for example, you can imagine this wave as moving forward, sometime later. You can imagine this peak here as moving in one direction sometime later. And you can imagine the in-between scenario as really kind of changes. You can imagine some of these dips turning into valleys and maybe flattening out a little bit and vice versa. So we need to, these snapshots are really great, but what would be really great is if we could animate our wave function. If we could get an idea of how the thing is oscillating and changing with time. Does it ever return to its original shape? Does it move back and forth? Does it split up into a million pieces? What does it do? So that's why we're interested in this wave function evolver code that we're going to be looking at. What I'd like to do is take a look at the code that I've already got. So I've kind of learned that these videos can start out kind of slow if I show you line by line me creating the codes. What I've done is I've gone ahead and created a code for a wave function animator. And I'd like to just go ahead and show you what it does, and then we'll start taking it apart. One of the things we have to define is the potential energy that we're interested in. In this case, we're going to be looking at a quadratic potential energy, also known as the harmonic oscillator. You'll see why we call it that in a few minutes. And we also have to define the initial shape of the wave function. And so here we've just got this exponential shape here. And actually, let's make this a little bit more interesting. Let's add in a plus 0.5 there. You'll see why in just a second. That's going to make it a little more interesting looking for our first go around. So and then there's more code beneath here that actually evolves the wave function. We'll take a look at what that does in a second. I want to give you an idea visually of what it does first. So here we're going to run the code. So what you've got on the animation here is three shapes. The red and the green represent the real and imaginary parts of the wave function. This thing psi, I didn't get into this earlier, but this thing psi is actually a complex function, meaning it is some number plus I times another number, where that I is the square root of -1. And so I can't really graph a complex number. So what I have to do is I have to show you the real part and the imaginary part, that first part, and then the part that gets multiplied by I. Now, both of those parts are changing with time. You can think of it as like having an X and having a Y, and both of them are changing with time. So one of them represents the real part, one of them represents the imaginary part. I'm going to be honest with you, I don't remember which color is which, but here's the beautiful thing is that it doesn't really matter, right? Because you could switch them and the wave will behave the same. Because what we actually are interested in is the probability density. And the probability density is this white piece here. This is what we call the modulus squared of the wave function. And it tells you roughly how likely the particle is to be observed in that region of space. So this is actually getting just a little bit complicated to maybe talk about. So let's maybe take out the red and green parts. So let me actually take out the parts where we are graphing the real and imaginary parts, just so that we have something a little bit more, a little easier to focus on. Okay, cool. So now when I run this, we should just see the white part. So this is the amplitude of the wave. So as you can see, it is bouncing back and forth, right? That's what you would expect for something in a quadratic potential. You'd expect it to sort of roll back and forth within certain bounds. So you can think of this sort of leftmost point and rightmost point as being the turning points of where it would oscillate back and forth in a classical system. You can see though there's always a little bit of tail leaking over here, because in quantum mechanics a particle has a probability of going where it's classically not allowed to go. And so this thing is oscillating back and forth. It's also changing width just a little bit, under the influence of it's being more concentrated on one side. It's being broadened out a little bit in the middle. And so this is the type of thing we're interested in looking at. We're interested in looking at how these wave functions and then the probability density change with respect to time. So if I add back in the psi real and psi imaginary parts, let's see, there we go. Then we'll get those red and green curves back. And actually, let's even find out which one is which. Okay, so for reference, I did set this up intelligently. The red is real. River red, river real. Cool. Although, as you'll be able to see, it doesn't really matter, because the red and green, they're sort of exchanging shapes, as it were. So when the red one is larger, the green one gets smaller. When the green one gets larger, the red one becomes smaller. The reason for that is that the total probability, right, if you take the total amount of probability of finding the particle anywhere, that number should be 1. It should be a constant. That's what we call the normalization of it. So that's what the program is calculating right here, is the normalization. And it's pretty dang close to 1, right? Out to 1, 2, 3, 4, 5, 6 decimal places. But what you'll also notice is that we have a warning displayed here that the normalization tolerance has been exceeded. Because this is an approximation, things can tend to build up or die down with our wave function. And so what we end up with is a normalization later on that is not equal to 1. In fact, it's significantly less than 1 or significantly greater than 1. So you can see the white shape is getting larger and smaller. Some of that's to be expected, but some of that is causing it to not be within an acceptable range of normalization of 1. And the reason for that is that we need to change some things about the approximation of the code. So this is where I need to talk to you about how the code actually works. So let's go back over to our whiteboard here. So the wave function obeys Schrodinger's equation, right? The Schrodinger equation is the cornerstone of quantum mechanics. You can't do quantum mechanics without it. The Schrodinger equation is to quantum mechanics what Newton's second law is to classical mechanics, or what Maxwell's equations are to electromagnetic theory. Parentheses, I know Lagrange's equation and Hamilton's equations are better for classical mechanics, but I'm just saying that to give an idea. Okay, so please don't lambaste me in the comments for leaving out Lagrange and Hamilton. Love Lagrange, love Hamilton. Anyway, back to the Schrodinger equation. The way the Schrodinger equation works is that you've got the wave function, and you've got its second derivative with respect to position. So you remember this thing is a function of position and of time, so I can take its derivative with respect to position or with respect to time. Writing out all the d by dx's and everything is a little complicated, so we're going to adopt a little notation from my PDEs class, where if you write down two subscripts to a function, it means taking a derivative with respect to that variable. So psi sub x means taking two derivatives of psi with respect to x. And then there's some constants out front here. We're not going to worry too much about those right now. This is just Planck's constant and the mass. There's a minus sign so that the thing behaves like an oscillating wave instead of like a blowing up wave, which really isn't much of a wave at all, I suppose. Plus, you've got the potential energy, which is a function we're going to assume just of position. You could make it a function of position and of time, but then things get a little bit more complicated. And that gets multiplied by the original psi. So this is psi without any derivatives. And on the other side, that's got to be equal to IH bar. So this right here is where the complex part comes in. If it weren't for this I right here, you could have your psi start real and stay real. But because of this I right here, it's got to be complex, right? It can't not be complex. And that gets multiplied again by the wave function, but this time with a derivative taken with respect to time. And it's only a single derivative with respect to time. So that makes this a little bit different wave function than you would see, for example, for an electromagnetic wave, where it's got two derivatives of position and two derivatives of time. So it makes this a very interesting wave equation. And so this is a partial differential equation, which is one of the hardest ones to solve in math. Not hard meaning time-consuming or tricky, hard meaning we have to invent new math to solve each one of them, or we have to invent approximation techniques. The approximation technique that this code uses is one called the finite difference method. This one works by taking each of these derivatives and approximates them using some sort of slope form. So for the first derivative, so for example for this time derivative, all we do is we say it's going to be the change in psi over the change in time. And the way we're going to work with that is that's going to be psi at your current time plus a little bit minus your psi at the current time minus a little bit, and of course I never draw my fraction bar long enough, divided by the change in time. So we're going from minus dt to plus dt, so that's being divided by 2 times dt. All right, so you take it at a later point, an earlier point, you make that dt very, very small, you end up with a decent approximation to the derivative. For the second derivative, you work out a little bit different math. I'm not going to actually go through all of that. I'm going to draw my fraction bar all the way across. The way this one works out is that you've got a psi at x plus a little bit of x. You've got a, let me check the sign on this before I go and quote this. All right, let's go. It is is psi. Okay, yeah. Okay, got it. This one's actually going to be plus psi, just the way the algebra works out, at x minus dx. And then you have to take minus 2 times psi at the current value of x. Now I've left off the x on here, so here you're keeping x fixed. And down here you're keeping t fixed. So I've abbreviated it for the sake of my screen there. And then, of course, you divide that by a dx. I suppose this has to be a dx squared, doesn't it? It's a dx squared or it's a 2dx squared? I don't remember which it is. It's one of the two. But the way that works out is that means that this is taking into account the information at the point to the right, at the point to the left, and at the current point. So there's there's this piece plus this piece minus 2 times this piece. So it's kind of you can think of it like a foiling type thing, where you end up with the one thing plus another thing minus 2 times the other thing. And so what the code does is it uses these to inch this thing forward 1 time step at a time. Inch it forward 1 step at a time. Second it forward 1 time step at a time. I don't think that has the same linguistic flair as inch it forward. Anyway, this is what the code implements. So that's what you can see down here. Basically, it uses the Schrodinger equation to involve the potential energy. So what you end up with is basically you end up with 3 different rays. You need a psi next value, you need a psi previous value, and you need the psi current value. And you need that at every value of x. That's why we've got this loop over ix. And the whole thing is being looped over time. So you've got all this stuff being taken into account. The potential energy, this is a long line of code right here. The potential energy finally ends up being involved here. So this is where the potential energy comes in. That is what makes one problem different from another problem. What you'll notice is that I've actually got this line written twice, one with psi imaginary and one with psi real. The reason for that is because this thing is complex. When you work this thing out, because this part is being multiplied by an I, that means that the real part over on this side of the equation is related to the imaginary part of this time derivative function here. And the imaginary parts over here are related to the real part of this thing. So the real and imaginary parts are sort of flipped and coupled, almost like on a Mobius strip, if you will. So that's why you have to have that twice. You also have to have it twice because that was a lot easier than trying to get VPython to work with complex functions, which I didn't explore into too great a detail as to whether it could do. It was just easier to have, okay, here's a function, they're both related, I promise. And so this is the main loop of the code. This is where it is iterating forward in time. It's also got to iterate across the space of the wave function. And so that's what this thing is doing. So with each little step in the animation, it is basically taking the entire set of values and evolving it forward in time. Now, of course, it doesn't take long for this normalization tolerance to be exceeded. So let's talk for just a minute about what this normalization tolerance is looking for. And then next time we'll talk a little bit more about how we can fix that and see whether there's anything we can do. The way the normalization works is that the total probability needs to be 1, meaning I need to add up the probability at each point. Well, that's an integral, or in a code, that's a summation. So the way that works is, let me find my normalization tolerance here. Okay, so the way that works is that you start out with, basically you want to get the area underneath the white curve. That's the psi mag curve. And so basically you start out with 0, and then you add to that each time the real part squared plus the imaginary part squared. That's how you get the white curves. You take the real part squared plus the imaginary part squared, and it's adding that for every value of x. So at each snapshot, it's calculating this value. At the beginning, it prints this integral for us, and so for ours, that was pretty close to 1, which is good. If it's not 1, we just divide all the values by the square root of that normalization value, and that normalizes it because that makes everything 1 because you're dividing the whole thing by its own area. So that's what it does at the beginning. Then it does the same thing later on. Basically, what it does is it does the same process. So it's taking the integral of 0, it's taking integral equals whatever you have calculated so far plus the current value squared plus the imaginary value squared. It does that for all the values of I. And then it has to multiply that by the dx, by the step that you're taking in order to turn it into an area. You've got to have height times length. And basically what it's doing here is it's saying, okay, the code is saying, okay, I know that this integral, this normalization value is going to vary. It's going to vary a little bit, right? Let's keep track of how high it goes and how low it goes. And if the difference in those becomes too big, if it becomes bigger than this norm tall that I've set up, which in this case I think was 0.1, I don't have that, oh yeah. I did not have that print. What do I have norm tall set as currently? Okay, I currently have norm tall set as 0.1. So basically, if these two become different by more than 10%, which is kind of a lot, for a system where we're studying a quantum mechanics problem, then it prints this warning. It says, warning, normalization tolerance exceeded, blah, blah, blah. You saw it earlier. And then it gives you some advice. Isn't that nice of the program to give you advice? Consider decreasing the time step or increasing the spatial step. This is where this becomes a little bit counterintuitive. If I go back up here to where we first have all of our parameters set up, we have our range of x values, right? So you want that to be nice and big, so that way the wave function can taper off. We've got the number of x values, so I've got 100 x points along the grid, which actually is not that much. If you look at the values of this thing, you notice that it's a little bit jagged. Let's see. So if I look at the actual values of this thing, I can see a little bit of jaggedness to it. Let's go ahead and close out of this. And you've also got to set the time step, the amount of time that it's moving forward. So right now it's moving at 0.001 units of time compared to the rest. And what the code does here is it calculates this epsilon value. I'm not going to go over the derivation of that, but this is a value that shows up in the finite difference equation. And basically, if this thing is too big, then the code takes too big of a step at a time. And that's where it ends up, missing important changes to the wave function. That's where the probability can get too big or it can get too small. And basically, this thing needs to be, reasonably less than 1. We've got an epsilon of 0.14, which is okay, right? So this thing is, you think of this as being like 14% or something like that, which is actually kind of big. So you got two ways of changing this. You can either decrease the dt value. You can decrease the time step, which is kind of intuitively makes sense, right? When we were doing the Euler-Kromer method last season, that's what we had to do to get the code more accurate, was decrease the time step. Or you increase the spatial difference. Now that seems counterintuitive because you would think that you would want your space to be more finely grained, but it actually has the opposite effect of making the code incur more errors. So one way we could do this would be to simply decrease the number of x points that we're evaluating at. So let's take a look at that. Let's see what happens if we make this, say, 50 instead of 10. So we're cutting that in half. So that's going to take epsilon and make it half the value, a quarter of the value, because the dx is being squared. So you notice we have a much better epsilon. Of course, you're probably not noticing that. You're probably looking at the wave function here, which now is much more jagged, right? We didn't have these jagged points before. So the results are not as nice. The results are not as pleasant looking with the dx. So there's sort of this tug of war between the two. But you notice this thing's been running for several seconds now, and we haven't had that normalization warning crop up. Let's try one more thing, and then we'll call it a day. Another alternative is to decrease the time step, right? So I can decrease the time step. Let's say I decrease that. Let's see. I decrease the last one by a quarter. So let's decrease this one by... actually, do I want to increase that or decrease that? Increase the spatial step. Yeah, sorry. Yeah, I did increase the spatial step by decreasing the number. Sorry. I had a little math moment in my brain. So let's try decreasing this one by a quarter. So let's take this one to 0.00025. So again, we won't get the, we did get the normalization tolerance, but this one was a lot better behaved, right? This one went all the way down to 0.933. This one stayed at 0.99999, but it went up to 1.223. So that's interesting. But we do get a much smoother curve. But of course, because I decreased the time step, this thing is moving much more slowly. I can alleviate that a little bit by changing the rate here. So let's try increasing this by a factor of 4. This is the number of iterations that the code goes through per second. But the code can only run so fast, right? So I can give it a rate of, 5 million, and it might have a cap of, say, 1,000. So increasing it to 1 million is not going to do a whole lot of good. So really what I have to do is I have to, sort of come to a compromise on these two. Okay, so I say, okay, maybe that is too small. I can make that a 0.05. And then maybe I can decrease this from my nx from, say, 500 to, I had 100 before. That's right. Maybe I can change this. Oh, that's why that one changed. Oops. I changed that to the wrong nx. Let's try that again. My bad. I thought it looked smoother. I didn't question it. I should have questioned it. Anyway, so here we get to about the same result. So the normalization does not spit it out. Whereas this piece here, is still smooth like it was before when we had nx equal to 100. It's moving a little bit slower though, so I can also make a compromise. And let's say make this one, let's make this one 800 and make this one 0.0, let's say 4. Whoa, and that gave me a serious problem. What happened there? Oops. Got something out of range. Oh, no, wait, I had 100. Excuse me, I meant 80. Excuse me, 80. My bad. Let's try that again. Okay, there we go. That's better. And so there I get a little bit better compromise. It's moving a little bit better clip. This thing is still a little bit jagged, but I haven't had my normalization warning pop up. So that's been pretty fun. I think what we'll do next time is we'll take a look at some different initial wave functions, start getting into more of the physics of it, and then we'll start playing around with the code. We'll try some different potential energies, make sure this thing is working up to the spec that we want it, because what I would love to do is to extend this thing from being one spatial dimension to 2 spatial dimensions. That's going to require some major reworking of the code. So thanks very much for watching. See you next time. Bye-bye.